Shan, I assume you know what that is.
It's a checker.
Yeah. Sort of a strange question, but what is the meaning of a checker?
It's a marker for a game.
Yeah, it's a marker. Right now, it has no meaning at all because the checkerboard isn't there, right?
Mm-hmm.
Okay.
Right.
Actually, you and I are going to assume that that's a bit, the tiniest piece of information.
Okay.
And depending on what's around it, it can take on all kinds of meaning. For example, if I put it there, what is the meaning of the bit?
It's a period.
And it means?
The end of a sentence.
The end of something, right? Yes.
Yeah.
Okay. So you take up the bit.
Okay.
And now put it down there. You know where you can put it? Right there. Now what does it mean?
No, it's a decimal point.
Which means?
It separates whole numbers from parts of a number.
Right. Okay, take up the bit.
Okay.
You know where to put it now?
Yeah, right there. It's part of a question mark.
And the meaning of a question mark?
And is asking something.
Yeah. And notice how the dot has to have this extra thing around it in order to make the idea of a question. Okay, now you need two. Here's one. Now what are the meaning of the bits?
No, it's a division sign.
And that means?
You're dividing this number into that many parts.
Okay. And if without the bits there?
It's a minus sign.
See, it could be bits like that in a row, you see.
Right.
Okay, and then it would be a minus sign. Okay, take up the two bits and put them down there at the end.
No, it's a colon.
Yes, which means?
You usually put them when you're going to start a list of something.
Well, a list, I like to think of it as an equal sign, that whatever's on each side of it is sort of equal.
Okay.
And by the way, if there were only one, it would be a period again, right? Okay, take up the two bits, and now put them down any place you like there. Now, what do they mean?
Now they're musical notes.
Yeah. What's the meaning of that one?
That's a G, and that one's a B.
Also, notice that they don't have any flags or anything sticking up, so it means what?
That they're whole notes.
A whole note, right. In fact, here's a whole bunch of little bits. Look at them all.
Oh, yeah, there's lots of them in that.
Yeah. Now, they have flags sticking up on them, too.
Yeah, the flags change how long
you hold the note, right. So that's sort of the visual version of a whole bunch of bits. Here's a slightly different version. Look.
It's one of those little piano things.
Yeah, and the dots, what do they mean here?
The air goes through the holes and makes music.
And makes music, yeah, right. So you see, it really depends on what's around the little tiny bit, what it's actually meaning is. Now, would you please read this for me?
This is what blind people use, isn't it?
Yes, it's Braille, right.
It must be hard to learn how to.
As a matter of fact, a friend of
Read it
mine
with
took
your
a look at it and said, gee, it's hard to read, and then realized that after all, blind people can't read, see it, you know, so that they have to feel it. And it's easy to feel,
But
even
you
though
gotta know
it's,
what they mean.
yeah. Well, here's the alphabet.
Oh, neat.
Yeah.
They're all different dots.
Right. So you could rub your finger along here and get the ABCs, and after practice a while, you could now maybe read some of these. So why don't you take that along home with you and see if you can practice reading Braille. Now, scientists and engineers have used the binary system with a series of bits. You know what binary means?
No.
Binary means two.
Okay.
And in this case, the bit is either on or off. And here's sort of a variation of it. Here's a column. When there's a bit in that column, like that, it means a 1. Okay, so put a 1 down there.
So what about that one? That would be 0, right?
That would be 0, so put a 0 there.
Okay.
Right. Okay. Now, if there's a bit in that column,
That would be 2.
that'll be 2. I'm now going to give you a very difficult problem. Can you put a 3?
Would be a 2 plus a 1.
Very good. 2 plus 1. Okay, it's 3. Okay, now do a 4.
This one right here. 'Cause
All right.
That's the 4 column.
5.
4 plus 1.
Next.
6 would be a 4 and a 2.
Next.
that would be, a 7 would be a 4, a 2, and a 1.
Mm-hmm. 8.
And 8 would be just here because of the 8 column.
Now, don't forget, in a computer, in the actual mechanism inside a computer, in the little chips, this is happening at the speed of light. So it's done very, very quickly, and the adding, subtracting, multiplying, dividing are all done in this sort of system.
That's neat.
Now, you probably don't think about it, but when you look at a picture, you're very often looking at a series of bits, and depending entirely upon what's around each bit, it has new meaning. In fact, there's a picture over there, see?
Oh, it's a tennis ball.
Yes. However, take a close look at it, and you'll see what?
The whole picture's made up of little bits.
The little tiny bits,
and they're all different shades.
The different shades and whatnot in order to create the impression of the bit. So if somebody asks you what a bit is, what are you going to say?
It's the tiniest piece of information, and it can make...
And its meaning?
Its meaning depends on its surroundings.
And so far we've seen what?
It can be a period.
Period.
Or a question mark, or musical notes, or it can make a picture.
Or part of a binary bit, or make a picture. Very good, yes.
Wow! I never heard this before.
Yeah, it really is a sort of nice sound, isn't it?
Yeah.
Do you know what's making the noise?
Probably when you put your put on some rosin and you...
Yeah, I put some rosin on my fingers.
Yeah,
and what happens when I stroke the rod?
It makes this high-pitched sound and starts vibrating.
Well, that's because I'm vibrating the rod up and down like this. And that's what makes the sound. Yeah, I think it's kind of a nice sound. How would you describe it?
It sounds like feedback.
Well, I don't think this is sort of feedback. This, I think, is pretty because it has a nice melodic sound.
Yeah?
Don't you agree?
Yeah.
Okay. You take back your feedback explanation?
Uh-huh.
Okay. Now, if you want to try this at home, you get an aluminum rod just from the hardware store, and you get some steel wool, and you rub it on like this in order to get rid of all the oil, and then rosin on your fingers, or you can put it on a leather pad like this if you want, and then stroke the rod, not too hard, just sort of gently to get it going, and you try it. Go ahead, see, Wensley, how you do it. Beautiful, very nice. Okay, not feedback, right? A beautiful sound. This weird vehicle is for carrying TV cameras and scientific instruments for exploring the surface of Mars. It's one of the designs underwritten by the National Aeronautics and Space Administration. The special carts used to explore the moon were driven by the Apollo astronauts, but no humans will be sent to Mars. It's impractical to steer around every small boulder from a control center on Earth because the radio signals take 30 minutes to make the round trip to Mars and back. Scientists and students at the University of Arizona believe their Mars ball will be able to navigate the rock-covered surface of Mars. The machine is compact enough to fit into a spacecraft. After landing on the surface of the planet, it would be inflated. In place of wheels, it has 2 sets of airbags that form large tires at each end of a single axle. A computer opens valves and starts pumps that fill some of the compartments with air. As the bags fill up, they push the vehicle along at a top speed of 1 meter a minute. Though it sort of lumbers along here on Earth, its builders believe it will work well in the thin Martian atmosphere. One of the many designs for an unmanned Martian vehicle, one that blows up its own tires to move forward. The Mars Ball. So what do you see there, Kelly?
3 bottles with water in them.
And I suspect, Kelly, that you suspect that it's not just water.
Yes.
Because I wouldn't have you come over just to look at 3 bottles of water.
Yeah.
As a matter of fact, shake that bottle 3 times.
Okay. It's turning purplish blue.
Yes. Try the next one.
Okay. It's turning too.
Try this one. Look what happened. What kind of a shaker are you anyway? Go give that one 3 more shakes.
Okay.
What's the matter with you? Look at that one.
I don't know how this is going back.
Right. That one's almost. You ready to give it
Yeah.
another shake? Go ahead. Now, ordinarily, when you have a chemical change like this, you add something to the chemicals. Did you see me add anything?
No.
What's in this jar right here?
Water.
Oh, well, it's a solution at least, right?
Yeah.
Liquid of some kind.
Yes.
Okay. What's between my fingers?
Nothing.
Take a deep breath.
Oh, air.
So what's in this bottle?
Air.
A liquid and air, right?
Yeah.
Okay. The blue color comes from a chemical called methylene blue that is an indicator and indicates the presence of oxygen in the solution. So when you shake it up, you're adding that invisible oxygen to the solution, and the methylene blue indicates it there. Then slowly the chemical reaction takes place to remove the oxygen so it gets clear.
Yeah.
Okay, shake it up. Now what are you adding?
Air and water.
Air, and actually it's the invisible oxygen.
Yeah.
Okay, try it, keep going. This is an example of a reversible chemical reaction. And you could keep on doing that for maybe half an hour. It would keep changing back and forth.
Yeah.
Okay, you got time enough for a whole half hour?
I guess.
Okay, well, you don't really have to. Just keep shaking. There, oh, that one's clear. Okay, try that one. One way to kill weeds is to spray them. Unfortunately, chemicals that are strong enough to kill weeds can affect other plants and animals. At the University of Illinois at Urbana-Champaign, scientists are testing a weed killer that's triggered by light. In tests, a concentrated dose of amino acids is sprayed on the plant, which is then covered with foil so that it gets no light. In the dark, the plant absorbs the chemical. Since the amino acid loses its strength in 24 hours, it should be environmentally safe. In the future, when the herbicide can be produced economically in large quantities, farmers could spray the weeds at night. This time-lapse sequence shows what would happen when the sun comes up. The plant on the left has been sprayed. When it's exposed to light, it withers and dies because of the weed killer triggered by light. Brian, here's a 25-watt bulb. And over here's a 75-watt bulb. Which is going to be the brighter?
Well, the 75-watt bulb,
Okay, how much brighter?
I'd say 3 times brighter, because 25 times 3 equals 75.
Makes sense, doesn't it?
Yeah.
Well, you and I are going to actually measure the brightness to see if you're correct. And we're going to do it with the help of a drop of oil.
How's that going to help?
Well, you'll see. First of all, I'd like you to put the drop right around that pencil dot. Okay, now swish it around and make it a sort of a little circle.
Is that big enough?
That's close enough. Okay, now I'm going to hang it here in the center of my meter stick. See the meter stick I have on the table down there? Mm-hmm. But it's got 0 right here where I'm hanging the drop of oil. Okay. Now I can move it so it's exactly at 0. Now I have some covers to cover over the light bulbs so they're not so bright. You want to put the other one over there? Okay. Now I'll turn it on, and you'll see what happens to the spot of oil.
It's darker.
Why, do you suppose? Think about this. When light hits the piece of paper, most of it is reflected back. But the drop of oil lets some of the light go through.
Because it makes the paper thinner.
Well, it doesn't make the paper thinner, but it fills in the spaces between the fibers of the paper and allows the light to go through, so that's why it looks darker. Okay, now I'll cover that one up. And now what happens to the spot of light?
Now the spot of light's lighter than the paper.
Than the paper, right. Now, in this case, most of the light, or quite a bit of the light from this bulb over here is being reflected back from the paper, but a lot of it is going through. That makes the spot lighter. So using this technique, we are going to be able to move these two lights back and forth until the spot disappears. Then you'll be able to measure their brightness by their distance. So let's take the 25-watt bulb and move this at 20 centimeters. According to your idea, where should the 75-watt light be?
60 centimeter mark.
Okay, 20 times 3 equals 60. Okay, you want over here and get ready to move this back and forth, but obviously the light in the room here is going to affect this. So first of all, I have my special switch. I'll turn out the lights. Now what does the spot look like?
Okay, it's too dark.
Okay, what does that mean you have to do?
Means that I'll have to move it back.
Okay.
Now it's too bright.
Okay, someplace in the middle. Move it back and forth until you find it where it shows the least.
That's about it.
About there? Okay, let me turn the lights back on again. And I'll turn these out so that we can... This one still is at 20 centimeters. What's that one?
It's near 50.
So what does that mean?
Means that watts don't measure brightness.
No,
but
they
they must
certainly-
measure something else.
Well, they measure the amount of electricity that the bulb uses. So a 75-watt bulb does not give 3 times as much light as a 25-watt bulb. And congratulations, you figured it all out with a drop of oil. Hey, you look nice in the in your safety
you do
glasses.
too.
We have safety glasses on because we're taking water apart.
How do you take water apart?
Well, you do it with electricity, but first of all, do you know the chemical formula for water?
Yep, H2O.
H2O, good, Christina. What does it stand for?
Hydrogen, oxygen,
Right.
and 2 stands for the hydrogen has twice as many molecules than
As the oxygen.
Yeah.
Right, there's the so if we're collecting the gas, hydrogen, and oxygen in these 2 test tubes by running electricity through the water here, which test tube has the hydrogen and which test tube has the oxygen?
This is oxygen and this is hydrogen. Because this has more space for gas.
Right. So we're collected more gas in this
Yeah.
one, right? Okay, now let me turn it off because over here I have collected test tubes of the hydrogen and oxygen. And can you put all the oxygen on one side and the hydrogen on
Okay.
the other?
This is hydrogen.
How can you tell?
This has more space for gas.
Okay.
This
full of
is-
gas.
Yeah. This is oxygen
How can you tell?
because it doesn't have as much room for gas.
Right.
And
It only has
some
half
water.
as much gas, okay?
This is oxygen too. This
For the
is
same reason, I assume?
Yeah.
Right.
This is oxygen. No, hydrogen.
Hydrogen, okay. Now, there's a chemical test for both hydrogen and oxygen, and it's kind of tricky. So here's what we're going to do. You take this little splint,
Okay.
and I will light it like this, okay? Then, when I bring this test tube over here, you blow it out and let it glow, and then you put the glowing splint down into, and don't touch the liquid, just put it up on top here.
Okay.
Okay, what happens when something goes from burning in air to burning in oxygen, do you know?
It bursts into flames.
Right, it gets hotter, right?
Yeah.
Because there's more oxygen to support the combustion. Okay, so let's try it. Wait until it gets going. Okay, now blow it out. Now stick it in here. There you go.
Start another fire.
That definitely, now you can blow it out. That definitely was oxygen. Okay, now the test for hydrogen is just the opposite. And this time I'll have to turn it upside down because hydrogen is lighter than air. And I'll
Yeah.
light this again, and you bring the flame up here near the,
Okay.
the gas. Okay, thank you.
You're welcome.
Okay, are you ready?
Yeah. Explode.
It explodes, yeah. Now you want to blow that out? Now, the
That was
reason it explodes is we're combining the hydrogen with the oxygen in the air.
Oh,
Okay, now that you know the test, we've tested those 2. Let it keep glowing, because now what
Okay.
should happen if this is oxygen?
It'll burst into flames again.
Okay, try it. There it did, okay. Now here comes the hydrogen. What should happen?
It'll explode and pop.
There it did, okay. Now you can blow that out. Now, Christina, I don't know whether you probably have never done this before, but now we've taken water apart to get hydrogen and oxygen, and in this case, we combine the hydrogen with the oxygen in the air, and we put water together again.
That was fun.
Made some water by combining hydrogen and oxygen in the formula H2O. This is the wilderness along the coast of North Carolina, where an important natural predator was the red wolf. In this vast area, where once there were thousands of red wolves, there are only 3 pairs, and they were flown in by helicopter. Wolves are raised in a special compound run by the U.S. Fish and Wildlife Service in the state of Washington. Even though the animals have been living in captivity, they're still wild. Once captured, they remain quiet and can be thoroughly examined. One reason they died off in places like North Carolina was their tendency to interbreed with coyotes. The offspring were a hybrid strain that simply could not survive. At a second sanctuary, operated by Washington University outside St. Louis, scientists took samples of blood from red wolves. Dr. John Patton analyzed their blood and the blood of wolves living in Washington to identify those that were pure red wolf. 6 purebreds were selected from both Washington and St. Louis to be flown to North Carolina. Special pens had been constructed in a wilderness area to hold the wolves for 6 months before they were released into the wild. In time, the wilderness of North Carolina could again have the benefit of one of its important natural predators, the once nearly extinct red wolf. Sarah, you want to pour some of this blue liquid into the glass, about 2-3 centimeters.
Sure.
Okay, that's enough. Now, here are some pieces of dry ice. You know what it is? Solid carbon dioxide. It's okay. Put a chunk, go about like that, in the glass.
Sure.
Have you worked with litmus in class?
Yeah.
Well, how does it work?
Well, when we put the blue litmus to an acid, it turns pink.
Mm-hmm.
But when we put pink litmus to a base, it turns blue.
Okay. So that you can find out whether how acid or base something is by whether it turns one way or the other. But what we are using in this glass, in this pitcher, is called a universal indicator. One liquid will go on the blue side if it's a base, all the way to yellow if it's an acid. In fact, what was it when blue when we started? Look what color it is now.
It's green.
Yes, it's green. That's about neutral, halfway between. And when it, now watch.
I can guess this. It's an acid.
Right, an acid. So pour in some more. Pour in some more base. You're going to change it back to, that's enough. I'll put in some more dry ice in order to get, the reason it's changing color is because as the dry ice changes to a gas, some of the gas dissolves in the liquid and makes it an acid. There's an acid already. Here, put in some more base.
Doesn't take very long.
Well, it depends on how much acid or how much base you put in and how much acid we create by the amount
CO2?
of carbon dioxide. There it is again. Okay, pour some more in. A little more this time. You can see why it's called a universal indicator, because it indicates both acid and base. See how it's green now?
Yeah.
Okay, now go ahead,
Acid's
fill the
more.
glass practically up.
Okay, that means a lot more vapor coming
Now
out.
a lot more base. Okay, that's enough. Now I'll add a little more solid carbon dioxide to make it go a little faster. And we will now have foaming. You know, this is what they use for mad scientists and stuff in the movies.
Mad scientist movies.
But this time we're using it for a very practical purpose to indicate whether something is a base or an acid by the universal indicators. Now green and now yellow.